Welcome. So the topic we'll be discussing in this lecture is M-way search trees. So there are two types of M-way search trees we'll be discussing. One is B trees, the other one is B plus trees. So in this lecture we'll be focusing on B trees. Right. So this will be the flow. First we'll be discussing the introductory part, like why should we go for another type of search trees called M-way search trees when there are already different search trees we have learned, like binary search trees, AVL trees, red black trees, and what is the need for M-way search trees, that we'll be discussing first. Okay, and then we'll be defining what is an M-way search tree, and also we'll be discussing like what are the properties of an M-way search tree, when we can say a tree as an M-way search trees, that we'll be discussing. After that we'll be discussing uh, a special version of M-way search trees. Okay, or you can say that B trees and B plus trees are balanced M-way search trees. Okay, B trees and B plus trees are balanced M-way search trees. Okay, like how we say that AVL trees and red black trees are balanced binary search trees. Similarly, B trees and B plus trees are balanced M-way search trees. Okay, so 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 that will be the flow, right? Okay, fine. So let us start with the introduction. So in introduction, basically we'll be discussing, or I'll be trying to address the need for M-way search trees. Okay, so previously we have discussed about binary search tree, AVL trees, red black trees. Okay, so for a balanced binary search tree and for AVL trees and red black trees, because AVL trees and red black trees are balanced binary search trees, the search, insert and deletion complexity, time complexity is of the order of log n. We know that, right? So this itself is a remarkable accomplishment. This itself is a remarkable accomplishment. That is, it is a quite a bit improvement in the what you call in the time complexity of the algorithm. Okay, then 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 why we need another search tree which is called as M-way search tree. Okay, the reason is with respect to memory access. With respect to memory access, AVL tree and red black trees are not doing great. So here RBT, actually I have mentioned this as a short form of red black trees. Okay, so AVL trees and red black trees are not doing great with respect to memory access. That is, our objective is to decrease the memory access. You should not increase the memory access, it should decrease the memory access. The extent to which the memory access is reduced, to that extent the speed can be increased. Okay, why in the sense, a typical memory access, here memory in the sense I'm talking about main memory. Okay, the time required to access a memory will be 100 times that of required to perform an arithmetic operation. Okay, if for example if CPU can perform an arithmetic operation in 1 millisecond, then probably it may take 100 milliseconds to fetch a data from the main memory. Okay, so the cost is 100 times I mean the cost in terms of time is 100 times as that of performing an arithmetic operation to access an memory location. Okay, so this is with respect to memory. But if you take the disk access, hard disk or any secondary storage device, the time required to access a disk by the processor, it will be 10,000 times that of a typical arithmetic operation. Okay, right? So for an arithmetic operation, if a system, if a processor needs X amount of time, then to access a particular data from the disk, it will need 10,000 into X amount of time, right? Okay, so what is expected? So what is expected in the sense, the extent to which we reduce the memory access and the extent to which we reduce the disk access, to that extent the speed of the processor will increase, right? Okay, So why this is happening? Why it is taking 100 times that of the arithmetic operation to access a memory location? Because there is always a speed mismatch between the processor and the main memory. Processor works at a very greater speed, but the main memory cannot cope up with that particular speed, right? Okay. Because of that reason, and another high speed memory is introduced between the processor and the main memory, and this memory is called as cache. Okay. So we have a high speed memory in between processor and the main memory. So this high speed memory is called as cache. Okay. So if you have the CPU here, and then cache will be somewhere here. Okay. The cache will be somewhere here, right? Right. Cache is here, and main memory is somewhere here. Okay. So main memory capacity will be huge, but the cache capacity will be less. Okay. Main memory capacity will be huge, but the cache capacity will be less, but the speed of accessing cache will be very fast when compared to that of main memory. Okay. So for CPU, we assume that CPU can access the content from cache in no time. Okay. That is, we assume that CPU can access the content from cache in no time. That is it is almost as if it is not spending any time at all. Okay. But that is not the case for accessing the content of main memory. Okay. Right. Now if you see the main memory is divided into several blocks. Okay. If you take the entire main memory, the entire main memory will be divided into several blocks. Okay. Maybe it may be divided into 100 blocks or 200 blocks or 128 blocks or 256 blocks, whatever it may be. Okay. Each block is a collection of word. Each block is a collection of word. One block may be equal to 4 words or 5 words or 6 words or 10 words. That depends. That vary with processor architecture to architecture. Okay. Or memory architecture to architecture. Okay. So each block will have, say, n words. Each block may have n words. Okay. Again, what is a word? Again, what is a word? The word size also varies with computer to computer. Okay. In some computer, the word size may be equal to 16 bits, that is 2 bytes. In some other computer, the word size may be equal to 32 bits, that is 4 bytes. In some other computer, the word size may be 64 bits, that is 8 bytes. Okay. Right. So on and so forth. Okay. It varies. The word size varies from computer to computer. Okay. So a block is nothing but a collection of word, and the size of the word varies from computer to computer, but generally the size of the word will be a multiple of bytes. Okay. Generally the size of the word will be multiple of bytes. Okay. Even, okay, 8. So here 8, here if it is 8 bytes from a word, then it is 64. Okay. So if it is 12 bytes, okay, if it is 12 bytes, okay, sorry, if 12 bytes from a word, okay, then it is 256 bytes. Okay. So 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 the block size is something like, it will be of the order of 100 bytes. Okay. Maybe 128 bytes or 256 bytes. Okay. So the size of the block, okay, it will be several words, but in terms of bytes it will be some 100 bytes. Okay. Right. So why we are learning all these things? In the sense, actually this is connected with the speed of the processor. Okay. And it is connected with the algorithm, right? The way in which you write the algorithm, because of that the speed may get reduced or it may get increased. Okay. To understand that, we are trying to understand what is happening exactly, right? Okay. So the key point is, the block size will be of several words. Okay. And the size of the word varies from computer to computer. Okay. Right. So uh, so so what happens in the sense, so the size of the word varies from computer to computer. Okay. So 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 each byte, okay, I mean each block, so each block may occupy several hundred bytes. Okay. Each block may occupy several hundred bytes, right? Now AVL tree and red black tree cannot take advantage of this. Okay. AVL trees and red black trees cannot take advantage of this. Okay, see 12 bytes, if a word is 12 bytes, then it is uh, then it is totally, it is 96 bytes. Okay, I told 256, no, it is 96. Okay, so you can just multiply by 8, whatever it may be, right? So this is what I'm trying to say. The word size changes from computer to computer, but the and and typically you can say that the block size will be of the order of 100 bytes. Okay, but the problem with AVL and red black tree is it cannot take the advantage of this cache memory. It cannot take the advantage of the block size of the cache memory. You see the block size of a cache memory. So the block size of the cache memory is of the order of 100 bytes, right? Okay. But if you take a typical node size, if you take a node size in a AVL tree or a red black tree, each node will have only one key value, right? It will have one key value and two pointers, because it is a binary tree. It's basically a binary search tree. So each node can have only one key and two pointers. So to store this one key and two pointers, hardly you may need how many bytes? Okay, you may need in C, if you need, if you see in C, if you take this, may take 4 bytes. Okay, right? Each of this pointer may take 4 bytes. So it is 4 plus 4 plus, it is only 12 bytes. You need only 12 bytes. Okay, so what happens in the sense, this 12 bytes in one block, it will hold only 12 bytes. Okay, that is one node details will get into one block. Okay, right? So that doesn't mean that we are not using the uh, remaining bytes of that particular block. Maybe it may contain some other data. Okay, but typically a node, each node will be stored in one block. Okay, each node will be stored in one block, or you can say that the nodes in a particular level of a tree, say the level 1. Okay, whatever the nodes in a level 1 will get into one block normally, and the nodes in the next level, the set of nodes in the next level may get into next block of, may be probably stored in the second block of the main memory. Okay, these two uh, nodes, and the nodes in the third level, probably stored in the another block of the memory. Okay, right? So what is that? Why? Okay, so these four nodes may be stored in this particular block of the memory, right? Okay, I mean the next block, right? So what's the problem with that? The problem with that is in the worst case, each of the nodes, okay, or the nodes in each of the level may be stored in different blocks, may be stored in different blocks of the main memory. Okay, and assume that none of the blocks are in the cache memory, and assume that none of these blocks are currently in the cache memory. Okay, and the block size of the main memory and the cache memory will be same. Okay, see, I told the main memory is divided into blocks. Okay, but the cache memory also will be divided into equally the same block size. Okay, if the block size of the main memory is 100 bytes, then the block size of the cache memory also will be 100 bytes. Okay, cache memory also will be divided into blocks, right? But the main memory can hold many blocks. Probably the main memory, if it is capable of holding 200 blocks, okay, cache memory may be hold, or even 2000 blocks. Cache memory may be able to hold only 128 blocks or 256 blocks at a time. Okay, so the number of blocks that can be held by the main memory will be more when compared with the number of blocks that will be held by the cache, because cache is relatively smaller in size, but it will be very fast. Okay, right? So now the point is, assume that the nodes at different level are stored in different blocks of the main memory. Okay, and let us assume that none of the blocks are in the cache memory. Okay, and in the worst case, a node will be available. Say you are performing a search operation. In the worst case, the value may be available in the leaf node. If it is available in the leaf node, then how many comparisons you have to perform? Obviously, you have to perform log n comparisons. Okay, or let us assume that tree level is 5. In this case, the tree level is 5. If it is 5, then it has to perform 5 comparisons. Now none of these blocks are in the main memory, so it has to perform the memory should be accessed 5 times. So memory should be accessed 5 times. For the first block, CPU will check the cache. It is not in the cache, so fetch the first block from main memory to cache. Compare, is this is the one? No. Then again fetch the block of the second level. Okay. Every time when the search goes in a binary search tree or in an AVL tree, we'll go to the next level, right? Or in a red black tree. Okay. So check that. No, it is not. Again fetch the uh, I mean the third block, I mean the node from the third block, check, no, not this. Again fetch the node from the fourth level, check, no, not this. Again fetch the block from the main memory to cache. So here fetching means what? Fetching from main memory to cache. Okay. So totally like that we are doing how many memory access? We are performing 5 memory access. Okay. So actually which is a very costly operation, and here if you see, the processor is spending most of the time on memory access rather than the actual calculation, right? So this is given with an example here. Assume that you have an AVL tree with this many nodes. Okay, with this many nodes, 10 lakh nodes. Okay, 10 lakh nodes are there. Then what will be the maximum height of the AVL tree? Not minimum height. We are asking the maximum height. Okay, so AVL tree is a balanced binary search tree with these nodes, with this many nodes. What is the maximum height possible? But still it should be an AVL tree. Okay, still it should satisfy all the properties of an AVL tree. So how to calculate, in the sense, that is given by this particular formula. Okay, you can remember this. So you may get this type of questions in exam. You should be able to answer. Probably the value given will be very high, something like this. Okay, if the AVL tree contains this many nodes, then what can be its maximum height? You have to just plug into this formula. It is floor of 1.44 into log n plus 2 the base 2. Okay, fine. So now I'll show you like how to calculate this in a calculator, in a Windows calculator. Okay, in a Windows calculator, how you can calculate this, that I will try to show you. Fine, 1 minute. Yeah, there it is. Yes, got it. Okay, so how to calculate this log to the base 2, in the sense, actually in the Windows calculator you have to select the scientific calculator. There is nothing like log to the base 2. You can see here you have log and ln. I think this ln is natural log. You have this. Okay, but this can be done with this ln. Okay, what you have to do is, whatever the value you want to calculate, okay, for that you take the natural log. Okay, you take the natural log and divide that by the natural log of 2. That is what you have to do. Okay, so it is 10 lakhs. Okay, it is 10 lakhs. In our case it is n plus 2. Okay, n is 10 lakhs, so 10 lakhs plus 2. Okay, right? So it is 10 lakhs, 10, total 6 zeros. Okay, 10 lakhs plus 2, right? So for this I am taking natural log. Okay, that is some value 13.8 something. Divide this by natural log of 2. Okay, natural log of 2. Okay, as a result what we are getting 0.69 something. Multiply this by 1.44. 1.44. Okay, so what you are getting is 28.7. 28.7. We have to take the floor of this. Floor means you have to go to the lowest integer possible. So the lowest integer is 28. Okay, so the result is 28. Okay, so with this number of nodes, how many levels are possible? In the sense, 28 levels are possible. Okay, right? So in the worst case, what happens? In the worst case, if you want to search a particular key value, there will be 28 comparisons. Okay, and if each of the and if the nodes in the different level are stored in different blocks of the main memory, then there will be 28 memory access. Then there will be 28 memory access. It means that most of the time the processor is spending in memory access. Okay, which is not advisable. So is there any way to reduce this? If you want to reduce this, then you have to decrease the size of the, decrease the height of the tree. Okay, the height of the tree is, the height of a BST is controlled by this. This is the minimum height that is achievable by a BST. Okay, log, again it is on the same formula, log n plus 1 to the base 2. Okay, you can fetch any number and you can check. Say for example, a node has a tree has 15 nodes. Okay, say a tree has 15 nodes, then what is the minimum height of a BST or AVL or a red black tree? Okay, then you can use the same formula. So 15 nodes, in the sense it is n plus 1, so 15 plus 1, so 16. Natural log of 16 divided by natural log of 2. Okay, divided by natural log of 2, right? Is nothing but 4. Okay, so you can check a node with level 4, a node with a height 4, it can have maximum how many, I mean a tree with a binary tree with a height 4, maximum how many nodes it can have? It can have 2 to the power 4 minus 1. 2 to the power 4 minus 1 is nothing but 16 minus 1, 15. Okay, right? So this is to do the reverse thing. Okay, so the height is actually controlled by this particular parameter. So is there any way to reduce the height? So we should reduce the height. Okay, so or what you can do is, instead of reducing the height, okay, we should also try to reduce the height. One thing is reducing the height, and the another thing what you can do is, otherwise you can increase the degree of the node. Okay, but if you increase the degree of the node, then the number of children will increase. Okay, so if you remember, we started with a normal tree where there can be many number of children. Okay, but implementing that will become very complex, and then we recognized that any tree can be represented in the form of left child right sibling format, and that can be further converted to left child right child format. So any tree can be converted to a binary tree. So with that understanding only, we entered into the concept of binary tree. Okay, but now with respect to this memory restriction, we are feeling that if the degree is more, if the degree is more, uh, then there will be that will be an advantage. So how it will be an advantage in the sense? Okay, so we are going to think slightly in a different way. The degree should be increased. So our objective is that we should we should take the advantage of the cache memory. Okay, so in the cache memory, if the block size is 100 bytes, if the block size is 100 bytes, then our one node size also should be 100 bytes. Okay, that is, one node should not have one key value, it should have more than one key values. Okay, it should have more than one key values, so that whenever I move a node, I'm not going to move only one value, I'm going to move a set of values to the cache memory from the main memory, right? Okay, so with that, if the set of values are moved, then with that it will be used for not only one comparison, it can be used for several comparisons. Okay, right? So here we are going to increase the degree of the tree, but we are going to increase the degree of the tree in some other style. Okay, right? So what we are going to do in the sense, in a binary tree normally we have only one value in a node. Okay, but in a m-way search tree, a tree can have more than one key values. Okay, a tree can have more than one key value. Okay, say for example, a tree has this many key values: 1 2 3 4 5, okay, 6 7 key values. Then it can have how many pointers? Any guess? Then it can have 8 pointers. Okay, if you take a binary tree has one key value. Okay, it has one key value, then it can have how many pointers? 2 pointers. That is, it can have 2 children, right? And each of these children again will have one key, and it can have 2 children. Okay, so in a tree, if a tree can support n values, okay, that means if a node in a tree can support n values, then it can have, or I will put it in another way. If a node in a tree can support n minus 1 values, if a node in a tree can support n minus 1 values, then it can have n childrens. Okay, that is it can have n pointers. Okay, so this node, if it can support 7 values, 7 key values, then it can have 8 pointers. So these will be the pointer one. Okay, all these are the pointers. Okay, so like this it can hold 8 pointers, right? 1 2 3 4 5 6 7 8. Okay, so now with this, what is the advantage in the sense, whenever, so this is one node. Okay, so this node will be stored in one block in the main memory. Okay, and whenever this node to be moved, you will moving this entire block, this entire node from the main memory to the cache memory. Okay, that is, you are moving the entire block from the main memory to the cache memory, and the part of the block is what, this node. Okay, so this entire node is moved, and this node contains, not now it is not having just one value, it is having 7 values, right? So at different places it can be used by the processor. It is not that once I am checking it is not usable. Okay, right, fine. So so right, so if a node in a tree has 8 childrens, if it has 8 childrens, then that is called as 8-way search tree. Okay, if a node in a tree can have 8 childrens, then it is called as 8-way search tree. Okay, so this is an 8-way search tree. So a node in an 8-way search tree can have 7 key values, right? Okay, so a node in an m-way search tree can have m minus 1 key values, and it can have at most m childrens. Okay, and it can have at most m children, right? Okay, so for understanding purpose, actually we are keeping lesser m values. Okay, but in reality, when the B tree is implemented, it will have actually more m values. It may have like 1000, 10,000 m values. Okay, because then only it will become equal to 100 bytes. Okay, because our objective is that the one node should fit one block of the main memory. Okay, then when you move that block, you are going to move that entire set of values, maybe 1000 values or 10,000 values. Okay, so that the searching for whenever you want to search something, you need not come back to memory every time, so that the memory access can be reduced. That is the whole objective. Okay, but for understanding purpose, we cannot take a node with so high values, so we will be understanding the concept of binary tree with a smaller value for m. Okay, we'll be understanding the concept of B trees with a smaller value for m, right? Okay, so this is the introduction. I think I have convinced. So the whole logic is, when you are using a red black tree or an AVL tree, in the worst case you may have to perform that many number of memory access that is equal to the height of the tree. Okay, and the processor may be spending more time on memory access rather than the actual calculation. So it means that red black tree and AVL trees are not able to take the advantages of the cache. Okay, so is there any way to ensure that the advantage of cache is taken? So for that, we are introducing the next type of tree, which is called as m-way search tree. So in an m-way search tree, a node can take more than one values. Okay, right? So if a node can take, if a node can have 8 childrens, then it can have 7 key values, right? Okay, so this is the motivation or the reason behind why we are going for m-way search tree. Fine. Okay, now let us see what is an m-way search tree. Okay, so as I have told earlier, a node in a binary tree or a BST can have only one value, and it will have 2 pointers. Okay, a node in an m-way search tree can have up to, okay, it is not that every node should have surely m minus 1 values. No, it can have up to m minus 1 values, and it can have up to m subtrees, that is m children. Okay, so m is called as the degree of the tree. So now m is the degree of the tree. So you know what is the degree of the tree? Degree of the tree is nothing but the maximum children a node possess. Okay, so the maximum children any particular node can possess in an m-way search tree is m children. Okay, so the degree of the tree is m. Okay, right? Okay, so every internal node, in every internal node there can be up to m pointers. Okay, maximum it can have up to m pointers, that is m children, and it can have up to m minus 1 key values. Okay, so this is the structure. So this is the structure of a binary tree or a binary search tree. So in a binary search tree, you have a value or a key, and to that you have a left a pointer to the left subtree or the left child, and a pointer to the right subtree or the right child. Okay, so there is one value and two pointers. Okay, whereas in an m-way search tree you will have m minus 1 values and m pointers. Okay, so here p0, p1 up to pn, all these are pointers. p0, p1, p2 up to pn. Okay, all these are pointers. Okay, so right, so all these are pointers. Okay, so here n is equal to m. Okay, here n is equal to m, right? Here n is equal to m. Okay, so there are n pointers or m pointers, so there can have, so each node can have up to maximum m children, right? And k0, k1, k2 up to k n minus 1 are the key values, right? And these k0, k1, k2 up to k n minus 1, all these things will be arranged in ascending order. Okay, is k0, k1, k2, all these things will be arranged in ascending order. That is, k0 will be less than k1, k1 will be less than k2, k2 will be less than k3, so on and so forth, up to kn minus 2 will be less than kn minus 1. Okay, are you getting? Why it is n minus 1? Because n is equal to m, so the number of key values will be n minus 1. Okay, right? So the key values are in ascending order such a way that ki will be less than ki plus 1. Okay, so where I ranges from 0 to n minus 2. Why we are saying 0 to n minus 2? If k is 0, you plug k is 0, then it means k0, that is key 0 is less than key 1. Okay, right? If I is 1, then it means that key 1 is less than key 2. Okay, so on and so forth. Okay, when I is n minus 2, that is key n minus 2 will be less than what? Key n minus 2 plus 1. Key n minus 2 plus 1 is nothing but key n minus 1. Okay, so this is the maximum key value we have up to n minus 1. Okay, because number of keys will be less than the number of keys will be 1 less than the number of pointers, right? Okay, so this is the structure of the m-way search tree. This is the structure of the m-way search tree, right? So m is basically the upper limit that defines how many key values can be stored. That is m specifies how many key values can be stored. It is not that m key values can be stored. So m means that m minus 1 key values can be stored. Okay, m children can be there. Okay, so in an m-way search tree, m specifies the upper limit. That is, upper limit in the sense the key values can be, the number of keys can be less than m. It cannot be equal to m, right? Okay, so if m is 8, then the number of key values can be up to 7. If m is 10, then the number of key values can be up to 9. Okay, right? So here is an m-way search tree with m is equal to 3. Okay, here is an m-way search tree with m is equal to 3. So m is equal to 3 means each node can have maximum 3 children. Okay, each node can have maximum 3 children. And how many key values? Number of keys, each node can have maximum how many keys? 2 keys, m minus 1 keys. Okay, so here m is 3, so m minus 1 is nothing but 2, right? 2 keys. Okay, so this is an m-way search tree of order 3. Okay, order or degree you can say. Okay, so instead of degree you can also call it as order. Okay, that is how many what is the maximum number of child a node can have. The maximum number of child a node can have is 3, right? Okay, so if you see the root node has two keys, 18 and 45. They are kept in ascending order and it has 3 pointers, 1, 2, 3. Okay, the pointer which is left to the 18, it is pointing to another node, and again this node has 2 values, 9 and 11, and it has 3 pointers. All these pointers are not pointing anywhere. It means it is null. All these pointers are null. Okay, then the pointer to the right of 18 in the root node, it is pointing to another node. Again this node contains 2 values, 27 and 36, right? So the pointer before 27 is not pointing anywhere. The pointer after 27 is pointing to another node which contains the key values 29 and 30. In this node also you can see there are 3 pointers. All these pointers are not pointing anywhere. Okay, so there will be a pointer before a key value and also there will be a pointer after a key value, right? So totally there will be if you have x key values, then there will be x plus 1 pointers. Okay, and the pointer after 45 in the root node is pointing to a node which contains two key values 54 and 63 and 3 pointers. Okay, out of these 3 pointers, the 2 pointers, the one before 54 and one after 54 was not pointing anywhere, that is they are null, pointing to null, and the pointer after 63 is pointing to another node which contains the key value 72 and 81, and here all the 3 pointers were pointing to null, right? So this is one example of an M-way search tree. Okay, fine. So this gives an introduction to M-way search tree. Now with this knowledge, let us go to B trees. Okay, so what is B trees? B trees are balanced M-way search trees. Okay, B trees and B plus trees are balanced M-way search trees. See, M-way search tree need not be balanced. Okay, for example, it can be of see here there is no node, maybe another level may be added here, maybe another level may be added here, like that. It may be of different, I mean different path can be of different height, and it need not be balanced. Okay, the M-way search tree, it need not be balanced. It is something like a binary search tree. Okay, binary search tree is not balanced, right? It depends on the way in which you insert the data. Depending on the way in which the data are getting inserted, it may be either balanced or imbalanced. Okay, but if you take an AVL tree or a red black tree, it will be balanced. Similarly, B trees and B plus trees are balanced M-way search trees. Okay, please remember, B trees and B plus trees are balanced M-way search trees. Okay, right. And a B tree of order M, a B tree of order M is a tree with all properties of an M-way search tree. Okay, that is a B tree of an order M for is a tree with all properties of M-way search tree. That is, it includes, B tree includes all the properties of an M-way search tree. In addition to that, it has its own properties that we will be discussing. Okay, so a B tree of order M, a B tree of order M will include all the properties of an M-way search tree. In addition to that, it will also have its own properties. Okay, what are the properties of M-way search tree? The properties of M-way search tree is, the main property is this only. That is, each node can have at most m children, and each node can have m minus 1 key values. Okay, right? So the root node also can have m children and m minus 1 key values, and that is also applicable to the leaf nodes. I mean the internal nodes. I mean the internal nodes also can have up to, what you call, each of the internal node may have m childrens and m minus 1 key values. Okay, and the key values should be in ascending order. Okay, that is, key 1 should be less than key 2, key 2 should be less than key 3, so on and so forth. Okay, fine. Now who introduced this concept of B tree? Okay, B tree is a specialized M-way search tree which was developed by Rudolf Baer and Ed McGrath in 1970s itself. Okay, so this Rudolf Baer is also the person who introduced red black tree. Okay, and he is also part of B plus tree also. So Rudolf Baer actually is the one who invented is involved in the invention of all the 3 trees: red black trees, B trees, and B plus trees. Okay, fine, right? So with this, I think we have set the stage for B trees. So B trees and B plus trees are balanced M-way search trees. Okay, a B tree of order M, it includes all the properties of M-way search tree, and also it has its own set of properties. So what are the properties of B trees? That's what we are going to discuss. Okay, so in addition to the properties of an M-way search tree, B tree has the following properties. What are they? Every node has at most m children. This is same as our M-way search tree. Okay, nothing different, right? See, the second property is important. Every node except the root node and leaf nodes has at least seal of m by 2 children. Okay, see, this property is important. Every internal node, that is the node except the root node and the leaf node. Okay, right? Every internal node. So here every internal node must have at least this many children. How many children? M by 2 children, seal of m by 2 children. Okay, so that is, if m is 5, okay, if m is 5, that is, each node can have maximum 5 children. This is the maximum upper limit. Each node can have at most 5 children, but every internal node should have minimum this many children. At least it should have this many children. How many? M by seal of m by 2. So m by 2, m is, if m is 5, then what is m by 2? M by 2 is 5 by 2 is 2.5. Okay, 5 by 2 is 2.5. Seal means go to the upper end. Floor means lower part. Okay, if you go to the upper end, so it is 3. 2.5. If you go to the higher end, it is 3. So it means that each internal node should have at least 3 children. Each internal node should have at least 3 children and at most 5 children. Okay, if the value of m is 5. Okay, that is a B tree of order 5, right? So by this property we are ensuring that the tree's height get decreased. Okay, by this property we are ensuring that the tree's height get decreased, because we are adding a condition that each internal node should have at least this many children, seal of m by 2 children. Okay, right. And the next property is the root node should have at least 2 children. The root node should have at least 2 children. Okay, for internal nodes this is the minimum count required. What is the minimum count? Seal of m by 2. Okay, and for the root node this is the minimum count required. It should have minimum 2 children. Okay, what is the maximum children supported for any node? It is m children. Okay, maximum children supported for any node, either root node or internal node, it is m children. Okay, and see, another important property is all leaf nodes should be at the same level. All leaf nodes should be at the same level. So this also ensures that, so this property, all leaf nodes should be at the same level, this ensures that the tree is a balanced one. The tree is a balanced one. Okay, are you getting? This will ensure that the tree is a balanced one, because you cannot have more height in one path and less height in another path. Such trees are not acceptable by B trees. Okay, so these are the 4 properties of B trees. What are they? Every node should have at least m children, and the internal node should have, every node has at most m children, and internal node should have at least seal of m by 2 children, and root node should have at least 2 children, and all the leaves must be at the same level. Okay, fine, right? A B tree of order 4 is given here. What is meant by order 4? Order means m is equal to 4. So m is equal to 4 means each node can have a maximum how many children? Each node can have maximum, they can have 4 children. Each node can have maximum 4 children. Okay, 4 children, and 4 children means how many key values? Each node can have maximum how many key values? It is m minus 1 key values, that is 3 key values. 3 keys are possible. Okay, right. And what is the minimum number of child that is allowed in the root node? That is fixed always. The minimum number of child allowed in the root node, minimum number of children in the root node is minimum, I'll call it as minimum child MNICH. Okay, minimum child that is allowed in the root node is 2. Minimum child that is allowed for an internal node, so I'll call it as internal node IN. Minimum number of children that is allowed in an internal node is what? It is m by 2, seal of m by 2. Okay, it is 4 by 2. 4 by 2 is 2. 4 by 2 is 2. So that is, minimum children should be 2 and maximum children can be 4. Right? Okay. Right? So root can have minimum 2 children. So here so if the root has 2 children, then it will have only 1 key value. Right? So you can see this tree, it has 1 key value, so 2 child. Okay. The left pointer, so the key value is 45. Right? It follows all the similar properties of a binary search tree. You can see here the node which is left to the 45, you can see it contains these values 29 and 30. 29 and 30 are lesser than 45, right? So it should be like that only in a B tree. Okay, because it is basically an extension of a binary search tree. It is basically an extension of a binary search tree. Okay. Similarly, if you see the nodes in the right side of 45, you can see it is 49. The key values are 49 and 63. They are nothing but they are greater than 45, right? Okay. So this node has 2 values, 29 and 32, and it has 3 pointers. Minimum it should have how many pointers? The internal nodes, it should have 2 pointers. It has 3 pointers, fine. And all these 3 pointers are pointing to something. So the pointer which is left of 29, it is pointing to this node which contains 18, 27. Again you can see the pointer which is left of 29 is pointing to these values 18 and 27, which is less than 27. Okay, the pointer which is after 29, it is pointing to these values 30 and 31, which are greater than 29 and less than 32. Are you getting? Because this pointer is coming in between 29 and 32, so it should point to those nodes. It should point to the node, and that node should have only values between 29 and 32. Okay, and the pointer which is to the right side of 32, it is pointing to a node, and this node contains the value 36 and 39, right? Similarly, the pointer to the left of 49 is pointing to a node which contains the value 46 and 47, which is less than 49. The pointer after the node 49 is pointing to the node with the key values 54, 59 and 61, right? 54, 69 and 61, which is greater than 49 and less than 63. This node, you can see it has three key values and it has 4 pointers. Okay, this is the maximum allowed. So maximum a node can have how many children? 4 children and 3 key values. So because we are discussing a B tree of order 4, it cannot have more than 4 children and more than 3 key values, right? Okay, and the pointer to the right of 63, it is pointing to another node which has 2 key values 67 and 72. You can see here this 67 and 72 are greater than 63, right? Also you can see that all leaf nodes are at the same level. Okay, there is no zigzag, okay, right? Say for example, there may not be this node at all, but then also all the leaf nodes are in the same level. Okay, this is not a leaf node, right? Okay, so it is not that every pointer should point to something. Okay, the point is all the leaf nodes should be, for example, if these two are not there, then also all the leaf nodes are in the same level, right? Okay, so this is the introduction to B trees. Okay, here I have given insertion, but it is not insertion, this is just an intro, right? Okay, when you will come to this insertion part later. Okay, first we will see the algorithm to search for any element in a binary tree, in a B tree, it will take order of log n times. Okay, that is fine. It is order of log n times, but now the node contains more values. Node contains more values, so the search will require less memory access. So in that context, the CPU time will increase, right? Okay, but still the complexity remains the same. It is order of log n. Okay, but in terms of memory access, the number of memory access will be reduced drastically. Okay, now we'll see how to insert an element in a B tree. Okay, so when you insert an element in a B tree, the insertion will always happen at the leaf node. We will not insert in the what do you call, in any other node. Either we will not insert in the root node or in the internal node. We will only insert in the leaf node. Okay, sometimes the root node itself may be the leaf node. For example, say the root node contains something, say 45, and there is no values at all, and there is no children at all. Okay, right? There is no children at all. Okay, so in that case, this itself is the leaf node. Okay, you may ask, leaf node should have 2 children. Okay, fine, it has 2 children, but both are pointing to null. That may also happen, right? It has 2, but both may point to null. Okay, so in that case, root node itself is the leaf node, so insertion may happen here. Okay, but otherwise insertion will happen only at the leaf node. Okay, and if you take a B tree of order 4, then a node can have how many key values? Up to 3. Okay, so if it cannot have more than 3 key values. Okay, so if a situation comes such a way that you want to insert one more key value, if you want to insert one more key, for example, you take this node, already 3 values are filled up. Say I want to insert one more value 62 also to this node. Now what will happen in the sense, this node will be split into 2 half. This node will be split into 2, right? The node will split into 2. Okay, so before inserting you have to sort it. So when you sort it, what happens? It will become 54, 59, 61 and 62. Okay, right? Then 54, 59, 61 and 62. Okay, then already it is sorted. Then you have to find the median element. Here there are 2 median elements. Okay, so if the count is even, there will be two median elements. If the count is odd, there will be only 1 median element. Okay, so in case of 2 median element, you can take any one of the median element. say you take this median element and push this to the parent, push this node value to the parent. Now this 59 will go here. Okay, it will adjust here. Okay, here if there is a space, the 59 will be accommodated here. This node is having only 2 key values, but a B tree of order 4 can have up to 4 key values. So this 59 will be accommodated here, 49, 54 and 63. Okay, right? But this node will be splitted into two. How it will be splitted? 54 will be one node and 61 and 62 will be another node. Okay, and this 59 has gone up, right? Okay, now 49's right pointer will point only to 54. 49's right pointer will point only to 54. Okay, and 54 is coming here in this place, right? There is no pointer here, right? And 54's right pointer will point, sorry, 59 is coming here, right? Yeah, 59 is coming here. 59 is coming here, right? Okay, 59 is coming here. Okay, 59's right pointer will point to 61 and 62, and 63's right pointer will as usual point to this. Okay, so this is how basically we do insertion. We'll discuss that in detail with example, but just I'm trying to give an overview, right? So the point is insertion happens only at leaf node. So whenever a node is inserted, you should always insert in the leaf node, but before inserting you have to check the maximum key values allowed in the leaf node. Okay, after including this new value also, if the number of key values is less than or equal to m minus 1, it is fine, it can be accommodated in that particular leaf node. If that is not the case, then initially you include that particular value and sort it and identify the median. Okay, and identify the median and push the median to the parent, again in parent you have to check the same process, whether parent is able to accommodate or not. If parent already has m minus 1 key values, it may not accommodate. If parent has less than m minus 1 key values, it can accommodate this. If parent already has m minus 1 key values, then again keep it in sorted order and identify the median and push it to the root node and push it to the next parent. Okay, so this process continues until it reaches the root node. Okay, after reaching the root node also apply the same principle. After reaching the root node also, you check whether root node can accommodate this or not. That is, if root node has less than m minus 1 key values, it can accommodate. Otherwise, split the root, otherwise include this new value, sort it and identify the median and split the root node into 2 halves and push the median value to the top, and now that will become the new root. Okay, so that algorithm, whatever I have told, that was explained here. Okay, first let us see the example, then this algorithm will be self understandable. Let us not go through that at first. Okay, so let us take this example. So let us take a B tree of order 5. A B tree of order 5 is given below. It is some at some state it was represented, right? We are not constructing the B tree from the beginning. Okay, a B tree of order 5 is given below. So this is the B tree which is given. In this you are asked to insert these values 8, 9, 39 and 4. Okay, so let us see how it works. So B tree of order 4 means what? Order 5 means what? Order 5 means each node can have at most 5 children. Each node can have at most 5 children, and each node can have at most 4 key values. The number of keys allowed is maximum 4. Okay, right? And root should have minimum 2 children. And the internal node should have minimum how many children? It is 5 by 2. The value of m is 5. Okay, so first you have to start what is m. So value of m is 5. So if m is 5, it can support each of the internal node should have how many? 3 children. Okay, it is seal of 2.5. Seal of 2.5 is 3, right? So each of the internal node should have minimum 3 children. Okay, fine. And all the leaves should be at the same level. So this is the state of the tree, and here we want to insert 8. Okay, so if you want to insert 8, you follow the binary search. Okay, so first you have to check whether you can see everything is in the sorted order. It should be in the sorted order. Okay, so here it is 18 is coming first value, so it means that 8 is already not here. Okay, So it should be in the left, it should be in the left of this particular 18 if it is there. Okay, so go here, go here, and if you see uh, here also it is not there. So and and actually 8 should come after 7. Okay, so this pointer is pointing to null, this pointer is pointing to null. Okay, so 8 should come here. Okay, so 8 should come here. Is there sufficient space in this particular node? This node can maximum accommodate how many key values? It can accommodate 4 key values, because here m value is 5, each node can accommodate 4 key values. So it can accommodate 8, no issues. So the tree will be just converted like this. Okay, so there is another key value included. Okay, right. So now how many key values are there? 3 key values are there, and there are 4 pointers, right? Okay, fine, right. So next we want to insert 9. Again start. So 9 is less than 18, so it should be here. So it's, but the pointer which is next to 8 is pointing to null, so it should come here. Okay, so can this node can accommodate? Yes, this node have currently 3 nodes. It can take, currently it has 3 key values, it can take up to 4 key values. So just add 9 after 8. So after 8 we are adding 9. Okay, so now it has 4 key values and 5 pointers. Now it is full, it cannot take any more keys, it cannot take any more keys. Okay, after 9 we want to insert 39. Okay, so in this we want to insert 39. So 39, if you see, it is greater than 8, it is less than 45, so it should come somewhere here. So this pointer is pointing here. Okay, so 39 is not here in this node, it is 21, 27, 36 and 42. Okay, so if at all 39 comes, it should come between 36 and 42. But you see, already you see whether this node can accommodate or not. No, it cannot accommodate. Why it cannot accommodate? Because already it has 4 key values. Okay, a B tree of order 5 can have maximum 4 keys, it cannot have more than 4 keys, so already it is filled. So now what you have to do, you have to just include and sort it. So if you include and sort it, it will become like this: 21, 27, 36, 39 and 42 and 42. Okay, now find the median. What is the median of this? There is only one median in this case, the median is 36, the middle number is 36. Okay, so if the total number of numbers are odd, then there will be only one median, otherwise there will be 2 median. Okay, so it is 36, so 36 you have to push to the top. Okay, push it to the parent, push 36 to the parent. Okay, and divide this into 2 nodes. Now 21 and 27 will become one node, 39 and 42 will become another node. Okay, right, and 36 will go here. So here, can 36 can be accommodated here? Yes, 36 can be accommodated here, because this node has only 3 key values and it can have up to 4 key values. Okay, so in this place 36 will come. Okay, and so here pointer is also there, but let us see, this is the before 36 there is one pointer here. It's not coming, you assume. Okay, after 36 there is a pointer here. Okay, right. Now, so this is, so 18, 36, 45, 42. Okay, right. Now the pointer left to the 18 is already pointing here. The pointer right to the 18 will point to this particular node, 21 and 27. Okay, right. And the pointer right to 36 will point to this particular node, 39 and 42. Because you can see 39 and 42 is more than 30, is greater than 36 and less than 45. Okay, and the pointer right to 45 will point to 54, 63. That is as usual. Then, so only this we have modified. This node we have split it into 2, and we have pushed this 36 to the parent. Are you getting? Okay, so this is how we will insert 39. Okay, when you are inserting 39, we are doing all these things. Okay, we have to, after inserting you sort. So every time after inserting we sort. Okay, it will be only inserted in that sorted order. Even see here also, you see 8 is inserted after 7, it is not before 7. 9 is inserted after 8, it will be always inserted in a sorted order. Okay, so similarly, even if the capacity of the node is full, then also we will keep it in sorted order. Then we will find the median and push any one of the median to the top. Okay, if there are even totally if there are even number of values, then there will be two medians. Okay, then you can push either the left median to the top or to the right median to the top. Okay, if you push the left median, that is called as left biased. If you push the right median, that is called as right biased. Okay, in case of odd number of values, there will be only one median. Just push that median to the parent. Okay, fine. So you can see the resultant tree. This is whatever I have, whatever we have drawn here. The same thing is here, right? Okay, this is after inserting 39. Now what should we insert? 4. Insert 4. So when you insert 4, what happens? Here you have to insert 4. Okay. Now 4 is here. You have to start with the root. 4 is less than 8, so it will be somewhere here. Okay. So 4 should come here. It is less than 7, so 4 should some come here. But can this node can accommodate? No. Already this node has 4 values. M value is 5. So the maximum keys allowed is, the maximum keys I will represent as k, which is 4. So already it has 4 keys. So now again, so keep this in sorted order and find the median. So 4, 7, 8, 9, 11. What is the median? 8 is the median. 8 is the median. So push 8 to the top. Push 8 to the top. Okay. And so this becomes two separate nodes. 4 and 7 becomes one node. 9 and 11 becomes another node. Okay. 8 has gone to top. 8 has gone to top. Okay. Now again you see, so if 8 if at all the 8 is accommodatable, it will come here in the sorted order. Okay. But can 8 be accommodated here? No, because already this node is also full. This node has already 4 key values. It's a B tree of order 5 which can support only 4 key values. So again find the median. Here what is the median? 36 is the median. So push 36 to the top. So a new root will be created. A new root will be created, right? So the root will be now 36. The root will be now 36, and 36 will have 2 pointers, right? Right. So this is divided into two nodes. 8 and 18 will be one node. 45 and 42 will be another node. 45 and 72 will be another node. Okay. 36 is pushed to the top. Okay. Now 36 left pointer will point to this 8 and 18, right? 8 and 18. And 36 right pointer will point to this 45 and 72. Okay. Fine. 8's left pointer. 8's left pointer will point to this 4 and 7, right? 8's right pointer will point to this 9 and 11. Okay. 18's right pointer, as usual, it point to 21 and 27. Okay, right? 45's left pointer, as usual, it will point to 39 and 42. 45's right will point here. All these things are same, right? So this is the updated tree. You can see here 36 left, it's point to 8 and 18. 36 right, it point to 45 and 72. 8's left 4 and 7. 8's right 9 and 11. 18's right 21 and 27. Okay. So this is how we insert the node 4, right? Okay. So searching is as usual to that of a normal, what you call, binary search tree. Okay. For example, if you take this particular tree, you want to search 54, then start with the root node. For 54 is greater than 45 or less than 45? It's greater than. Go to the right subtree. Again 49, is it greater than 49? Yes. So go here. So is it but it is less than 63. It is greater than 49, less than 63. So it should be available somewhere here. Okay. So in this node you can search and find 54 is there. Are you getting? So this is how we locate, right? So similarly you can take any value, say 39. 39, first you start here. When you start here, you encoded 45. It means you have encoded a value which is greater than 39. So it means it should be in the left subtree. So go to the left. Okay. So when you search here, you have 29, 32, no other values. So it should be in the right subtree of 32. The right subtree of 32 is this. So if you start here searching 36, 39, yeah, 39 is here. So you have found it. Okay. So this is how we do searching, right? Fine. Now let us discuss how to insert into a binary, I mean in a B tree from the beginning. Okay. So let us take this particular case. Let us take this particular case. Consider this question. Construct a B tree of order 4. Construct a B tree of order 4. That is order 4 in the sense each node can have maximum 4 children and the number of key values allowed is 3. Okay. And these are the values are to be inserted in this order. Okay. 5, 3, 21, 9, 1, 13, 2, 7, 10, 12, 4 and 8. Okay. So the number of values allowed, maximum number of values allowed in each node is 3 key values allowed. Okay. And each node will have maximum 4 pointers. Right. So let us see step by step how it works. So first we want to add 5. So then there will be first we want to add where is that? Okay, first we want to add 5 or 3. Okay, first we want to add 5. Okay, first we want to add 5. So this is not 3, this is 5. Okay, this is not 3, this is 5. So first 5 will be added, right? First 5 will be added. So maximum a node can have how many values? 3 values, so that the other blocks I am leaving empty. Here the pointers I am not showing, but pointers are there. Before every node there is a pointer, after every node there is a pointer. Okay, that is understandable, right? So initially for this node the other 2 blocks are empty. It can hold, but currently it is not holding. Okay, now when you want to insert 3, so already we know that insertion happens only at the leaf node. Okay, so currently we have only one node, that is root node. So when you want to insert 3, it will be always inserted in the sorted order. It is not that 3 will come here. No, it will always come in the sorted order. Okay, so 3 will come first and then 5. Okay, and the next block is empty, right? Okay, next is 21. Okay, so 21, obviously 21 is greater than 3 and 5. So when you insert 21, it comes here, 3, 5 and 21. Okay, fine. And next what you want to insert? Next you want to insert 1. Okay, but can you insert 1 sorry, next we want to insert 9. Sorry, next after 21 we want to insert 9, but can we insert 9? Already this node is filled, already the root node is filled. There is no way we can insert 9. Okay, but still you have to, the algorithm, as per the algorithm you have to keep it, and then you have to split the node into 2. That is the process. Okay, so if at all you want to keep 9 here, where it will come? It will come after 5. Okay, so 3, 5, 9 and 21. So then you find the median. These two are the median. Okay, so let us take the first one. So let us go with left biased. Okay, so this is the first median, which is 5. So 5 should be pushed up. 5 should be pushed to the parent, but there is no parent, so a new parent will be created. Okay, so 5 will go up, and 3 will, and this node will be split into 2. 3 will be the one node, and 9 and 21 will be the another node. Okay, if you push 9 to the top, then 3 and 5 will be one node and 21 will be another node. Okay, that is, the splitting will be happen something like this. Whatever you push to the top, okay, push to the parent, and to the left will become one node, and to that right will become another node. Okay, so in this case we are taking 5. So when you push 5 to the top, 3 will become one node, and 9 and 21 will become another node. Okay, so 5 can take another 2 values. Currently it is empty, right? 3 can also take another 2 values, and 9 and 21, this node can take another 1 value, right? Okay, so this is how 9 is added into the tree, right? Then we want to add 1. Okay, so this is for adding, I'll draw here. This is for adding 9. Okay, when you add 9, this is how the 9 gets in. Okay, fine, right? So then we have to add what? After 9 we are supposed to add 1. Okay, so 1, just you check, 1 it comes in here. So you just recall, it should always, insertion will always happen in leaf node. Okay, so 1 comes here, but we have to insert in leaf node. This is not the leaf node right now. So just check whether 1, is it less than 5 or greater than 5? It's less than 5. So go to the left. So left is 3, node 3 is there. This is a leaf node, so it should be added here. So it will be always added in the sorted order. So first 1 comes, then 3, then one more empty space is empty position is available for another key value in this particular node. Okay, this is how 1 is added, right? Fine. Next, what should we add? Next we have to add 13. Okay, next we have to add 13. So So to this you have to add 13. So again when you want to add 13, you just check here 13, is it less than 5 or greater than 5? It's greater than 5, so it should come in the right side. The right side is there is a sufficient space. Yes, there is a sufficient space, but you have to sort it. So it will come as 9, 13, 21, because 13 is greater than 9 and less than 21. So it should come after 9 and it should be before 21. Okay. So this is how 13 is added, right? Next we have to add 2. Next we have to add 2. Okay. So this is 2. So again check here. 2 is it less than 5 or greater than 5? It's less than 5, so it should come to the left. So always remember insertion happens only in the leaf node. Okay. So is there a sufficient space here? Yes, there is a sufficient space, but it should be sorted. So 2 comes after 1 and before 3, because 2 is greater than 1 and less than 3, right? So we have added 2. Next we have to add 7. Okay. So when you add 7, what happens? 7 is greater than 5 or less than 5. 7 is greater than 5, so it should come in the right side. It should come in the right side of this tree. But is there a sufficient space? There is no sufficient space. Okay, but still you have to keep it in order, and you have to find the median. So when you keep it in order, it becomes 7, 19, 13, 21. So the median is what? 9 and 13. So we will go with left biased. So 9 will be pushed to the top. Okay, so 9 will be pushed to the parent. In the parent, is there a sufficient space to hold 9? Yes. So 9 will come here, and this node will be split into 7, and 7 will be one half, and 13 and 21 will be another half. Okay. So 5's right pointer will point to 7, and 9 will come here, and 9's right pointer will point to 13 and 21. Okay. So that is drawn here. It is drawn here. 1 minute, it is taking load, it is loading. So where is that? Yeah, so you can see here this 5 has gone to the top. Okay, 5 has 5 or 9 as per the previous diagram. 9 has gone to the top, and there is a space to accommodate that. Okay, but it should be sorted. Okay, so it is 5 and 9. Okay, but yeah, 5 and 9. Okay, sorry, I think I have opened the wrong one. Let me 1 minute. So the 12 should not come, right? Yes, this one. Okay, so this is the one we are getting after moving 9 to the top. So 5 and 9 will come here. Okay, so 9 will just come after 5. Okay, and 5's right will point to 7, and 9's right will point to 13 and 21. Okay, so that's what it is exactly doing, right? So this is how we insert which node. So this is how we have inserted the node 7. Okay, so after inserting 7, this changes has taken place. Okay, then we are inserting 10. Okay, so when you insert 10 to this, what happens? Always insertion should happen in the leaf node, remember. So if you check here, 5 is 10 is greater than 5? Yes. Then is 10 is greater than 9? Yes. So it should come to the right of 9. Okay, is there is a space here to the right of 9? Yes, there is one space. It can take 3 key values. Okay, it's a B tree of order 4, but you have to sort it. So it will come 10, 13 and 21, right? Okay, fine. So after adding 10, then what should we add? Then 12. So when you add 12, again check, 12 is greater than 5, 12 is greater than 9, so it should come in the right part of 9. But right subtree of 9, right, the right child of 9, if you see, it is already filled. Okay, so you cannot keep here, but we will keep it, and we'll keep it in ascending order. So when you keep 12 here, and if you put it in ascending order, it will become 10, 12, 13 and 21. So now these two are the median values, 12 and 13. So you have to push 12 to the top. Okay, so when you, that is, you have to push 12 to the parent. When you push 12 to the parent, can this parent accommodate 12? Yes, it can accommodate, because it can have maximum 3 values, right? And this node will be split into two halves. 10 will be one half, 13 and 21 will be another half. Okay, so 9's right pointer will point to 10, and 12's right pointer will point to 13 and 21. So that is the resultant tree. 12 goes up, 9's right pointer is pointing to 10, so this is one split. Okay, and 12's right pointer is pointing to 13 and 21. Okay, so this is after inserting 12. And then what you have to insert? Then we have to insert 4. Okay, so when you insert 4, so this is here. When you insert 4, what happens? So if you take this particular tree here, if you want to insert 4, 4 is less than 5, so you should keep here. But this child, if you see, it is already filled, so you have to just keep 4 here, and you have to keep it in ascending order. Then you have to find the median. So median will be 2 and 3. So that is what shown here. Median is 2 and 3. Okay, so we are following left biased, so 2 should be moved to the parent. Push 2 to the parent. Okay, but when you push 2 to the parent, if you see, this is also filled. This is also, parent is also already filled. Okay, but again keep it in ascending order, so it will become 2, 5, 9 and 12. It will become 2, 5, 9 and 12. Okay, so again if you take the median, 5 is the median, so 5 should go to the new parent should be created. There is no top before this. Okay, there is no top, there is no parent to the top of it. Okay, so 5 should go to the top, that is 5 should become the new parent. So if 5 becomes a new parent, 2 will become its 2 will be one split, and 9 and 12 will be another split. Okay, right? So 5 becomes a new parent, and its other two key locations are empty, right? And this 2 will be one split, and 9 and 12 will be another split. This node will be split into two halves. Okay, and 5's left will point to the node 2, and 5's right will point to node 9 and 12. Okay, again all this happened because of this. Okay, so when you move this 2 to the top, again this will be split into two halves, right? One will be one half, and 3 and 4 will be another half. Okay, so 2's left will point to node 1, 2's right will point to node 3 and 4. Okay, right? Rest of the things are same. 9's left will point to the same node 7, 9's right will point to node 10, 12's right will point to node 13 and 21, right? So this is how we insert node 4. Okay, now finally we have to insert node 8, lost. So when you insert node 8, you start with 5 here. It's greater than 5, so it should come here. Again it is this particular node. 8 is less than 9, so it should come here. So in this node, is there a space? Yes, so it will be added here. That's it. Okay, so I have not drawn a separate diagram for this, so I have just shown here. Okay, so it will be added here. So this is how insertion happens. Okay, right? So in our case, whenever the node is getting filled, we are getting totally whenever an extra node is added, extra key values added, we are getting even values, so that two medians are there. If it is odd number, then when you add an extra, if it becomes an odd number, then there will be only one median. In that case, you can just push that to the top or to the parent. Okay, so that's it about insertion. I want you to try this as a homework. That is, with the same values, the values are same, but you assume the order as 5. Okay, but you assume in our case, what is the order? In our case, the order is we have discussed. This is for order. What order we have discussed? This is for order 4, right? This is for order 4 we have discussed. Okay, so you take it as order 3. Okay, you take it as order 3. So order 3 means each node can have maximum 3 children. Okay, and each node can have maximum 2 key values. With this, you try to construct a B tree with these values, right? Okay, fine. Let us stop here. Yes, thank you.